Hello everybody, I'm Patrick Donnelly. I am the CephFS team lead at Red Hat. My colleague Jeff Layton couldn't make it to KubeCon this year, so he won't be joining me to give this talk, so you'll just have me. Today I want to be talking about a new technology we've been working on to have NFS servers deployed with the Rook storage operator with Kubernetes and have these NFS servers export the Ceph file system. So to begin, since many of you may not be aware of CephFS, CephFS is a POSIX distributed file system originally developed around 2005 by Sagewell to serve as a file system for HPC clusters for the national labs. CephFS is interesting because it uses the clients and the MDSs cooperatively maintain a distributed cache of the inodes and the directories. That is sort of a difference between many other distributed file systems where clients talk directly to servers and the servers manage all the state. This was a decision made early on to allow the clients to have direct access to the data without needing to go through any type of gateway. CephFS provides full failover management by the use of, for example, standby metadata servers. It also provides for horizontal scale out by having multiple active metadata servers serve in a cluster. The metadata servers do not maintain any state. They're very easy to containerize. They store all their state in Rados, Rados being a distributed object data store, which is the main underlying component of Ceph. On top of that, the metadata servers represent the metadata hierarchy and they present that to the clients for access. Clients directly talk to the object store when they're reading or writing to the file objects. In order to maintain consistency, the MDS hands out capabilities, which are similar to leases from the academic concept. They hand these out to clients, which allow them to delegate metadata authority to clients. In particular, they can allow clients to write to data or also buffer writes of data or cache reads, and do this safely in such a way that it doesn't conflict or is inconsistent with other clients. So moving on, the origins of this project actually began with OpenStack. There's two primary services within OpenStack that use Ceph. There's Manila, which is a file share service for virtual machines within OpenStack. And then also Cinder, which is a block device provisioner for VMs used primarily to create root disks for a virtual machine to boot from. And we've gone a great, have done a lot of integration with Ceph in this way. And Ceph has become one of the more popular storage technologies to use within OpenStack. Community survey done in the past, in a few years ago, found that CephFS was the primary storage provider for use within Manila. And the reasons for this, I think, are fairly straightforward. Ceph is a open source storage solution and is easy to incorporate into your OpenStack clusters, and then also it's free. So if I'm talking about OpenStack, then why am I here? Why are we talking about why should I be talking about Kubernetes? So it turns out that there's a big push right now, as we all know, that to manage distributed services within the context of a container orchestrator, in this case Kubernetes. And there's a lot of attractive reasons for doing this. Containers are lightweight and easy to deploy in response to changing application needs. Importantly, especially for this project, it allows for extensible service infrastructure, so I can deploy services in response to the changing needs of the application. Containers are also parallel enough to be, or lightweight enough to allow for easy parallelism. I can deploy a lot of containers in response to to those changing needs of the application. It's a much easier to do failover in a container orchestrating environment. Instead of having a dedicated machine that is there to take over when a service fails, I can just spin up a new container anywhere in my infrastructure to take over that role. And finally, Kubernetes also allows us to do fast IP failover management, which will become important later on in this discussion. Okay, so how we're using Kubernetes within Ceph is through the Rook storage operator. Within Ceph, there's now a big push to deploy most Ceph clusters in the future using Kubernetes and Rook. Rook is one of the main storage operators for handling storage within the context of Kubernetes, and Ceph is one of the primary storage systems that it supports. And the way Kubernetes, or the way Rook works within this context, is I can define now a Ceph cluster that I want to deploy within Kubernetes, and it's as simple as feeding it some YAML files into kubectl, and the Rook agents that are running on all the nodes will figure out where it can host object storage devices for Ceph, attaching an object storage device to available disk drives or SSDs on all of your nodes in your Kubernetes cluster, and then deploying the Ceph daemons as needed in order to get your cluster ready. The great hallmark success of this is that it allows you to deploy a Ceph cluster without knowing anything about Ceph, which has historically been a very difficult thing to do. Ceph, being a distributed system, had a lot of knobs to turn and a lot of upkeep to do on all of your different computers that are serving Ceph. And now with these storage operators, this is becoming easier than ever to host a Ceph cluster without knowing anything about distributed storage. So coming back to the subject of this talk, why do we want a NFS gateway in front of Ceph? So you may remember when I was talking about earlier, the primary use case for CephFS was for an HPC environment where we're running a lot of high-performance computing jobs that need access to fast file systems, especially, for example, for scratch space. And that was its target use case. And because of that, it was operating in a mostly trusted environment, and the application could be trusted to access the file system in a safe manner. In today's deployments in like OpenStack or Kubernetes, and how you may want to serve your infrastructure to various tenants, that may not be an assumption you can safely make. And there's a few reasons for that. It's not necessarily easy to restrict which types of clients are accessing your file system. You may have, for example, if I'm running with an OpenStack and I have virtual machines being brought up by my customers and they're running older kernels, it may not work without bugs against my Ceph cluster, and I lack control over what types of clients they're using to talk to Ceph. Another issue is security. You may want to firewall off your storage cluster, in fact you probably do, to prevent clients from having unrestricted access to your storage network. So there may be a firewall. Additionally, you may want to introduce some kind of authentication and authorization mechanisms, for example, through Kerberos, which Ceph does not yet support, and force clients to authenticate through those mechanisms. So moving on. So for that reason, it's attractive to put an NFS daemon in front of CephFS, NFS being a very common file access protocol within the industry, and put that in front of Ceph in order to serve as a gateway between the clients and the Ceph cluster. NFS Ganesha is an open source NFS server, and it runs completely in user space without any dependencies on the kernel. It's open source software licensed under the LGPL. What makes Ganesha attractive is that it provides a plug-in interface for multiple different kinds of exports, and then also provides support for exporting different types of file systems. The most obvious and usual case would be a local file system having NFS or Ganesha export something in the local file system, but within our case, we want to actually export the CephFS file system. To do this, Ganesha has these backends called the file system abstraction layer, and that abstraction layer for Ceph uses libCephFS to actually talk to the Ceph cluster, so any incoming NFS request RPC will be translated into a corresponding call through libCephFS. Correspondingly, Ganesha also uses libratos, which is a library that gives direct access to the object storage layer to store its various state that it needs to maintain in order to recover from a failover when a standby Ganesha takes over. It also uses Rados to now store its configuration files instead of using the etc namespace within, for example, its file system. And for these reasons, Ganesha is very amenable to containerization. We can store all of our all of the file system state is, of course, stored in CephFS. We can store all the configuration and recovery information within Rados. There's no need for a writable local file system. And so one of the things we wanted to have was scale out, and that is we wanted to have multiple Ganeshas be able to export the same CephFS file system, which is not as easy as you might think it to be, mostly for reasons of consistency. We want to be able to have a service that's containerizable, so that we could use it in the future work of containerizing Ceph for use in a deployment, container deployment orchestrator like Kubernetes. Additionally, we wanted to support a newer NFS protocol which has several, which notably allows for NFS clients to store state so that they can get better performance. And finally, the ability to talk to Ceph and Rados for all of this communication. No need for any type of third-party clustering software, for example, CLTDB, which has normally been used in the past for Ganesha to handle failover management. So up to now, Ganesha has been deployed in a passive-active fashion, and this has been available since Ceph Luminous back in August 2017. You have one NFS server, which all of your NFS clients talk to. And you use the third-party tools, Pacemaker, CoroSync, to handle the failover between the active NFS Ganesha daemon and the standby NFS daemon. The main drawback of this approach is that it scales poorly and it requires idle resources. You need a idle NFS Ganesha server available to take over when the active fails. And all of the NFS clients are talking to a single active NFS server for all of their data needs, which obviously will not scale very well. So one of our goals was to allow for all of these NFS clients to talk to multiple NFS servers. So why this is difficult to put multiple NFS servers in front of the Ceph file system in an active-active fashion is because of the NFS clients now having state. In particular now, in NFS v4, we have the clients are now given leases similar to CephFS capabilities, which allow them to read or write to files or hold locks. And the clients must now contact the NFS server during a lease period between 45 and 60 seconds. This had a few problems, mainly around failover of clients. And in NFS v4.1, which is the target protocol we're supporting, they now have a sessions layer added on for the NFS clients when they're talking to the NFS server, which provides exactly once semantics, so you don't, when you're retrying an operation, it doesn't happen multiple times. And now also a reclaim complete operation. So when an NFS server goes down and it comes back up, it begins a reclaim process where all the NFS clients can reestablish whatever state they had with the prior NFS server. That was, if you waited the entire lease period, that means nothing could actually happen in terms of I/O for any client of the NFS server. So they added a new reclaim complete operation, which allowed the NFS server to lift the grace period early. Moving on. So after an NFS server restarts or a server takes over for a failed NFS server, it has no ephemeral state because it doesn't store its state anywhere locally. And so all the clients have to notify the NFS server exactly what state they had. That includes what files they had opened, how they had the files open, any kind of locks they had. And because you don't want one client to say, I want to write to this file, and another client, which has not reconnected yet, has write access to that file and may be buffering writes, you need to wait a little bit to give all the clients a chance to reconnect to the server. And that's what this reclaim session period is 2 lease periods. Lease period corresponding to how long you wait for a client to say they're still holding on to a lease. So during that grace period, the NFS server can't issue any new state, and the clients may reclaim the state they had prior to the crash. And in fact, this method of recovering all of the state that you had open is very similar to what we do in CephFS. Moving on. So logically, this can be organized into a series of epochs where an epoch corresponds to the lifetime of a particular instance of an NFS daemon, beginning with a grace period where all of the NFS clients can reconnect and try to establish whatever state they had. And then you have, after that completes, the NFS server transitions into the normal operation, which will be generally a very long time. It should be in the normal operation. Failovers are not that common. So the observation is that we can use the same logical organization of the grace periods and the normal operations and have this apply to a cluster of servers. And why that's a difficult problem is that if we have multiple NFS servers exporting the same backing file system, they will, you may have state that's issued to one client of one NFS server, and during a failover event, another NFS client of the other NFS server may try to acquire that state. And so now we need to form agreement on what state has been issued and how to reclaim it. And so the way the NFS Ganesha handles that is through the use of coordinating grace periods. It has a central database and a Rados object, which keeps track of what the current grace period epoch is for all of the NFS servers, so that they can form consensus on when the grace period should happen. So all the NFS servers together in the cluster will enter grace period together whenever there's a failover event, so that none of the NFS servers accidentally issue state that another client that needs to reconnect to a failed NFS server needs to reclaim. So these are some details on how that works that I won't get into due to time, but I'm willing to take questions on it later. So the next challenge we had to address with this work is we wanted to layer NFS over a cluster file system. And because both of the protocols for CephFS and also NFS v4.1 are stateful and they use a least-based mechanism, you need some way to handle the case where an NFS server fails and another server wants to come in to acquire that state, and you need a way to make that failover event happen faster in the within CephFS. Namely, CephFS has its own timeouts that it maintains for its clients. Whenever a client fails and comes back, that client has a certain amount of time to reestablish its session with CephFS. Likewise, all those NFS daemons, all the NFS clients have a certain amount of time, corresponding to the lease periods, to reconnect to the NFS daemon to reestablish their state. And there's some conflicts, or there's some overlap there in time, which can cause a very long delay for the NFS clients to reestablish their state and be able to continue the normal operations they want to perform. And how long it takes for the NFS server to reacquire the state it needs in CephFS. So one of the new features in Nautilus was that we allowed a client to reclaim the state of a prior session. When a CephFS client dies abruptly, the MDS will keep its session around for several minutes, allowing that client to come back and say, I'm still here, and I want to reclaim all of these, the capabilities that I had, all the file locks that I had. And then with the presumption that these clients have not actually failed and come back as a brand new client, there was simply a network partition that separated them from the MDS. And for a while, this was fine enough for a kernel client, which if it were to restart, it wouldn't be trying to get a new session with MDS. It would or it wouldn't try to reclaim the old session with MDS, because all the applications that were running with the kernel client have also been rebooted, so it just gets a fresh state. It's the same thing with CephFuse, which is another alternative mounting mechanism for CephFS. With NFS Ganesha, we have this new problem where the NFS daemon has state that it's issued to the clients, and if the daemon fails and comes back, it needs to reacquire all that state that it had in the prior session. So now in Nautilus, CephFS supports a CephFS client to come back and claim all the state that it had in a prior instance of the client without knowing immediately what all that state was. During the grace period for the NFS server, the clients will come in and say what state they had with the prior instance of the NFS daemon, what files I had open. Correspondingly, the Ganesha server will talk to CephFS and reestablish the state that it had from the prior session. When all of that is complete, it actually completes the session similar to the reclaim complete operation that the NFS clients send to the NFS server. So our next challenge is the deployment and management of NFS clusters. Now we have all of the basic mechanisms in place to build a cluster of NFS servers that are in an active configuration. Now what we need next is a trivial or a simple way to deploy those NFS Ganesha servers in an active configuration dynamically, corresponding to whatever kind of load we have on the on that particular export of the CephFS file system that the NFS clients are accessing. And then also we want to scale in another direction where we have an NFS cluster for each export in the CephFS file system we have. So keep in mind the CephFS can be a very large file system with billions of inodes and many different users with different use cases and applications. And so we want to be able to have an NFS cluster front each subtree within CephFS corresponding to the application need. And all of those, and then you've achieved a few things by doing that. You improve performance because now you are isolating certain file system behaviors with a group of NFS cluster daemons. You're improving the caching of the NFS daemons because now you have applications that are all accessing the same NFS servers. And you can also improve security because now I can isolate the cluster of NFS daemons based off of which application should be using them, and furthermore isolate which parts of the CephFS file system tree that the NFS daemons have access to based off of what applications will be using those NFS clusters. Finally, another challenge we need to address is IP migration and failover. So when an NFS server inevitably may die for some reason, we need a way to spin up a replacement very quickly and cheaply. And also, we need a mechanism to migrate an IP address from the prior instance of the NFS server to the new instance. And these are historically difficult problems, but not anymore, and the reason for that is Kubernetes. It's fairly simple to spin up new containers in response to failover, and also you can migrate the IP address to the new pod. So this is where Rook and Kubernetes come in. Rook now supports in the version 1.0 release that just came out the ability to specify a Ceph NFS resource type, which will launch the NFS Ganesha servers in response to the kubectl command creating those objects. And Rook and now Ceph have a deep integration with each other between the Ceph Nautilus release, which was just released about 2 months ago, and Rook itself. So now Ceph is also extensible with Rook in that it now is able to deploy services in response to the changing application needs, for example, creating a new file system. by talking to Rook and saying, I need another metadata server, please spin another container up. And this has all been abstracted away very nicely, and we are able to use this to have the manager daemon deploy NFS clusters in response to what the user specifies via the how they specify the NFS cluster for their file system. Furthermore, we can scale up the NFS cluster up or down in response to how the application needs change, and have this all centrally managed from the manager. In the future, we also want to use this to as sort of a holy grail type concept within CephFS. We've always thought it would be very nice to be able to deploy more active metadata servers in response to the changing load of the file system. We also plan to use the same idea and apply this within CephFS as well to scale MDSs. So in summary of this work, we've built several mechanisms that are available today to deploy these NFS clusters in front of Ceph. Now we have this ability to create volumes and subvolumes, volumes corresponding to separate Ceph file systems, which multiple Ceph file systems are not yet supported within Ceph. That's something we're planning to do in a future release. The more common thing to do is to have this subvolume concept where you separate or you dedicate an entire directory tree to a volume which may be exported to a particular virtual machine or a set of containers for sharing. And then this allows Manila for OpenStack or the CSI interface for Kubernetes. All of your pods can use the same interface to talk to or to set up, configure volumes, and then also configure the exports of those volumes. The other mechanism we have finished and built is the Rook and Ceph integration. So now Ceph can launch these NFS clusters dynamically and configure these NFS clusters to have a set of exports and configs corresponding to these subvolumes. And finally, we've updated NFS Ganesha to be cluster aware and have faster and correct recovery with Ceph file system. As far as vision for the future, again, we have all these mechanisms built. What the next stage of our work is to actually make this very turnkey in terms of actually configuring the volume and then setting up the NFS Ganesha cluster. So in version 14.2.2, the next version of the Ceph Nautilus, Ceph Nautilus release, you'll be able to create these subvolumes through a centralized command. And then in a subsequent future release, we're planning to make it very simple to actually deploy an NFS cluster in an active fashion in front of Ceph with Rook and Kubernetes, just with a simple command enabling NFS and setting various configuration options you might want to have. For example, what kind of NFS or network namespace you want to attach the pods to in terms of, say, for example, if I have OpenStack virtual machines that have been set up and I want to attach my NFS Ganesha clusters to the same network namespace that those tenants are in, then I can configure that through this command, and then finally turn it on by just setting share NFS to true. Furthermore, we also want to add support for NFS with the NFS version 4 migration of clients. So we want to be able to not just expand the size of the NFS cluster, but then also shrink it. And that involves shifting all the clients of the NFS server that you want to remove and have them move on to one of the remaining NFS servers within the cluster. And then finally, optimizing the grace periods for subvolumes, because right now all the NFS clusters are within the same logical cluster in terms of grace periods, when that may not be necessary because subvolumes within CephFS may not share any inodes, so there is no shared state between subvolumes. It would be better for the NFS server clusters to be isolated from each other and not enter grace periods together, because there would be no conflicting state between them. And then finally, it would also be nice to use this for SMB. So that's all of my time. Thank you for your attention and coming to my talk. I'll take any questions.
The I/O from NFS client and NFS server communicate with Ceph, so the I/O they share the same network.
So the NFS clients may be on a different network namespace than the storage one is.
I mean for NFS server.
Yeah.
So NFS server, NFS server have two networks.
Yes, it would have two networks.
Oh, okay, sorry.
Which requires newer features, as I understand it, in Kubernetes, to be able to enable having multiple network namespaces attached to a pod. This has not historically been possible. Any other questions? Okay, thank you for your time.